It was built to last 5 years. It has now been flying for 47. And in the cold dark at the edge of everything, running on a power supply, shrinking by 4 watts every year, sending home a signal so faint it takes the largest radio antennas on Earth to detect it, Voyager 2 has been making discoveries that nobody predicted and nobody fully understands. Not the discovery of volcanoes on Io, not the discovery of geysers on Neptune's moon Triton, not the extraordinary findings from its planetary grand tour that rewrote every textbook on the outer solar system. Those were stunning, but they were discoveries made in familiar territory, in the solar system we had been theorizing about and modeling for centuries. What Voyager 2 has been finding since it crossed the boundary of the solar system entirely and entered the space between the stars is something different in kind. It is finding that the universe at the edge of everything we call home does not behave the way anyone thought it would, and some of what it has sent back from out. There has left the scientists receiving it with more questions than they started with, staring at data that the models they built over decades of careful work simply did not predict. Voyager 2 is the only spacecraft in history to have studied all 4 of the solar system's giant planets at close range, and it was the first and remains the only human-made object to fly past Uranus and Neptune. These are not small achievements. When Voyager 2 reached Neptune in 1989, it was the culmination of a 12-year journey across the solar system that had been planned with extraordinary precision, using the gravitational fields of each planet it passed to accelerate toward the next one. At Neptune, Voyager 2 discovered 5 moons, 4 rings, and the Great Dark Spot, a storm system the size of Earth embedded in Neptune's atmosphere, and photographed Triton, revealing it to be the coldest known planetary body in the solar system, with nitrogen ice volcanoes erupting on its surface. The images that came back from Triton that night are still among the most extraordinary ever taken by a planetary spacecraft. A world so cold that nitrogen freezes on its surface, with geysers erupting not from heat, but from the sun's faint light warming dark material beneath the ice. Nobody had imagined Triton before Voyager 2 showed it to them. After Neptune, the planetary mission was over. NASA formally renamed the entire project the Voyager Interstellar mission, and Voyager 2 followed a course below the ecliptic plane and out of the solar system. For the next 29 years, the spacecraft traveled outward through the heliosheath, the turbulent outer layer of the solar bubble where the solar wind slows, becomes compressed, and is eventually stopped by the pressure of the interstellar medium flowing inward from the galaxy beyond. It was a long, slow transit through territory that no instrument had directly sampled, and that existing models described with varying degrees of confidence. Scientists knew roughly what to expect. They had models, they had theory, they had remote measurements from Earth orbiting instruments, and the data Voyager 1 had sent back after crossing the same boundary 6 years earlier. They thought they were prepared for what Voyager 2 would find. They were not entirely prepared. On November 5th, 2018, Voyager 2 became only the second spacecraft in history to leave the heliosphere, crossing the heliopause, the boundary where the solar wind meets the cold, dense interstellar medium, at a distance of approximately 11 billion miles from Earth. The most compelling evidence of the crossing came from an instrument that Voyager 1 had lost 40 years earlier, leaving its heliopause crossing data permanently incomplete. Voyager 2 carries a working plasma science experiment, an instrument that stopped functioning on Voyager 1 in 1980, long before it crossed the heliopause. And this instrument provided first-of-its-kind observations of the nature of the gateway into interstellar space, observing a steep decline in the speed of solar wind particles at the moment of crossing, and then no solar wind flow whatsoever in the environment beyond. The solar wind that had blown outward from the sun for 11 billion miles, carrying the sun's magnetic influence across the entire span of the planetary system and far beyond, simply stopped. On one side of the boundary, solar plasma. On the other side, something else entirely. What Voyager 2's 5 working instruments recorded at and beyond the heliopause is the dataset that has been generating sustained scientific discussion and genuine puzzlement ever since. 5 research papers in the journal Nature Astronomy described what scientists observed during and since Voyager 2's historic crossing, each paper detailing the findings from one of Voyager 2's 5 operating science instruments, covering magnetic fields, energetic particles in different energy ranges, and plasma. The papers documented not a single clean surprise, but a series of them, stacked on top of each other, each one individually requiring an explanation, and all of them together requiring a wholesale revision of the models that had been used to predict what this boundary would look like. The first surprise involved temperature. Both Voyager spacecraft measured significant increases in local plasma temperatures as they crossed the heliopause, temperatures recorded in a region with ultra-low particle density, meaning the plasma is high energy but does not transfer heat effectively. The temperature at the heliopause boundary reached approximately 50,000 Kelvin, far higher than the models had predicted. This high-temperature barrier at the boundary region, sometimes referred to informally as a wall of fire, is not a solid object, but a region of energetic plasma where particle behavior and magnetic dynamics shift rapidly, and its existence revises the current understanding of how the solar system interfaces with the galaxy. The heliosphere's outer edge is not the relatively calm transition zone that previous models described. It is a zone of intense energetic activity, a thermal barrier between the warm, magnetized bubble of the sun's influence and the colder but higher energy environment of interstellar space. The second surprise involved the magnetic field, and it is the finding that has generated the most sustained theoretical debate among heliospheric physicists. Voyager 2's magnetic field instrument confirmed a surprising result that Voyager 1 had recorded 6 years earlier, that the magnetic field in the region just beyond the heliopause is parallel to the magnetic field inside the heliosphere. Before either Voyager crossed the boundary, the prevailing expectation was that the interstellar magnetic field, generated by processes in the wider galaxy rather than by the sun, would be oriented differently from the solar magnetic field that pervades the interior of the heliosphere. The two fields, solar and interstellar, were expected to meet at the heliopause in a kind of magnetic discontinuity, a clear directional change that would mark the physical boundary between the sun's magnetic domain and the galaxies. With Voyager 1, scientists had only one sample of these magnetic fields and could not say for sure whether the apparent alignment was characteristic of the entire exterior region or just a coincidence. Voyager 2's magnetometer observations confirmed the Voyager 1 finding, indicating that the two fields align. This confirmation is more troubling than it initially sounds. If the solar magnetic field and the interstellar magnetic field are parallel at the heliopause boundary, it means the two systems are connected in some way that the standard models do not fully account for. The heliosphere is not simply a bubble floating freely in an indifferent interstellar medium. Its magnetic field contained entirely within its own boundary. Something is causing alignment between the solar magnetic field and the interstellar magnetic field at the crossing point, a connection that implies physical coupling between the sun's magnetic domain and the galaxies at a level of intimacy the models had not predicted. Research published in 2024 suggests the heliopause may be shaped differently than once believed, offering a mechanism to explain the mystery of why the direction of the magnetic field did not change at the Voyager crossings. Instead of a thin boundary line as once thought, this newer work suggests a thick boundary layer where magnetic fields from the heliosphere and interstellar space interact, implying that Voyager may not yet be in the pristine interstellar medium until the thicker boundary is fully crossed. The third major surprise from Voyager 2's heliopause crossing involved the leakage of particles through the boundary, and this is where the two twin spacecraft produced directly contradictory results that forced a fundamental rethinking of how the heliopause works. Scientists had originally expected that particles from our sun would not leak out of the heliosphere into interstellar space, and Voyager 1 saw no such leakage when it crossed the boundary. But Voyager 2 found the opposite, recording a small trickle of solar particles streaming through the heliopause. Two spacecraft crossing what is supposed to be the same boundary found completely different results. Voyager 1 saw no leakage. Voyager 2 did. The heliopause, in other words, is not a uniform boundary with consistent properties everywhere around the heliosphere. It is a permeable, variable, location-dependent structure whose behavior differs from one crossing point to another. Voyager 2, which crossed the heliopause at a different position than Voyager 1, found that this flank region allows more particles to escape or enter. And both spacecraft recorded increased plasma density before and after the boundary crossing, suggesting compression on either side of the heliopause and indicating that interstellar pressure is shaping the outer layers of the heliosphere more actively than previously modeled. The implications of a permeable, variable heliopause extend beyond the scientific interest of the finding itself. The heliosphere is the shield that protects every living thing on Earth from the full intensity of galactic cosmic rays, the high-energy particles accelerated by supernova explosions, and other violent events throughout the galaxy that stream continuously through interstellar space in all directions. Inside the heliosphere, the sun's magnetic field deflects and attenuates these cosmic rays, reducing the flux that reaches the inner solar system to levels that life on Earth has evolved to tolerate over billions of years. If the heliopause is permeable, if it allows solar particles to leak out and interstellar particles to leak in at rates that vary with location and solar activity, then the shielding effectiveness of the heliosphere is not the constant, reliable property the standard model implied. It is variable, dependent on solar cycle, on the orientation of the interstellar magnetic field, and on properties of the heliopause boundary that we are only now beginning to map with direct measurements. Beyond the heliopause, interstellar space is a very different environment from the one inside the heliosphere, quieter but hardly quiescent, described by one researcher as a relic of the environment the solar system was born out of. It is space permeated by the accumulated debris of stellar processes stretching back to the formation of the galaxy, carrying in its magnetic fields and particle populations the signatures of supernova explosions, stellar winds from distant stars, and the slow chemistry of molecular clouds. In late 2023, Voyager 2's plasma wave instrument recorded multiple instances of density oscillations in the interstellar plasma, helping map the characteristics of the interstellar medium in the region of space the spacecraft was traversing. These oscillations, converted to audio frequency signals the way Voyager 1's interstellar plasma hum had been, represent direct measurements of the physical properties of interstellar space at a specific location, a data point that no remote sensing instrument can replicate because it requires being there. The power situation that frames all of this science has a particular kind of poignancy to it. Both Voyagers were still functioning in April 2026, but the radioisotope thermoelectric generators on each spacecraft put out 4 watts less each year. And because of this diminishing electrical power, the Voyager team has had to prioritize which instruments to keep on and which to turn off, with heaters and other systems shut down one by one as part of power management. In October 2024, NASA announced that Voyager 2's plasma science instrument had been turned off, preserving power for the remaining 4 instruments. The same instrument that had provided the definitive evidence of heliopause crossing in 2018. The same instrument that caught the solar particle leakage that Voyager 1 had missed, the instrument whose unique functioning had made Voyager 2's crossing data so much richer than its twins, was shut down to keep the others alive a little longer. By reanalyzing particle and magnetic field measurements from Voyager 2's 1986 Uranus flyby with modern techniques, scientists in 2023 and 2024 found clues that Uranus may be venting plasma from its bizarre magnetosphere, or even evidence of an undetected moon, showing that decades-old Voyager data are still yielding fresh insights when examined with 21st century analytical tools. The spacecraft is already gone, already billions of miles past Uranus, but the data it collected in 1986 is still being mined for discoveries that the computers of that era were not sophisticated enough to extract. Every archived transmission, every stored measurement from every flyby, is a resource that future analysis can return to with better tools and find things that earlier examination missed. Merav Ofer, a space physicist at Boston University who has spent her career studying heliospheric science, summarized what the combined Voyager findings have revealed about the structure we live inside. We know now how little we know about the heliosphere. It is way more complex, way more dynamic than we thought. That statement from a scientist who has dedicated decades to understanding exactly this system is the most honest summary of what Voyager 2's discoveries at the edge of the solar system have produced. Not a neat set of confirmed predictions, not a validated model. A revised appreciation of complexity, a recognition that the boundary between everything the sun controls and everything the galaxy contains is stranger, more dynamic, more variable, and more physically active than the models built from inside the heliosphere had managed to capture. Voyager 2 was launched when the people who maintain it today were children, or in some cases, not yet born. It was built with technology that a modern smartphone exceeds in computational power by a factor of billions. Voyager's computers process about 8,000 instructions per second. A modern smartphone yields more than 14 billion instructions per second. And yet this machine, with its 8,000 instruction per second brain and its 4-watt dimmer power supply and its 16.5-hour communication delay, has produced discoveries that rewrite the understanding of the boundary between our solar system and interstellar space in ways that 40 years of Earth-based observation and theoretical modeling had failed to anticipate. It is still out there. Right now, moving at approximately 35,000 miles per hour through interstellar space, its remaining instruments sampling the plasma and magnetic field and particle environment of the space between the stars, sending home data that will take 16.5 hours to arrive, carrying measurements of a place no other instrument has ever sampled. The discoveries it has already made at the edge of the solar system have been unimaginable in the specific sense that nobody imagined them before they happened. The discoveries still encoded in its aging instruments waiting to be transmitted and received and analyzed may prove equally unimaginable in the same specific way. The universe, at the edge of everything we call home, turned out to be nothing like the models said it would be. And a 47-year-old machine running on the power of a nightlight is the only thing that went far enough to find that out.